All right, so I think we can start now. I think we're over here. So I don't know if you guys been watching the videos on YouTube channel. We're done with the all like a 1 through 9 chapters. So I'm gonna talk about the chapter 10. So the first one is the nomenclature. So how are you gonna write the name of the compounds? That's the key. Beside all the common rule, there's couple more things I need to mention on this nomenclature here. Is we're gonna put some. So chapter 10 is about halogen. So whenever you have halogen groups, this is something you can do. Whenever you have a like bromine, chlorine, fluorine, all that core name, take the core name. So simply what you need to do, just try to remove the I and E at the end. So for example, if you have bromine, you can try to remove just take the core name here, and then take the brom, and just put O right next to it, O. So that will make a bromo. So same thing goes to the chlorine, fluorine, everything. So the chloro, fluoro, bromo, iro, it's all the same. So just core name plus O. That's how you can put the halogen as a substituting group. So for example, if you have this type of compounds over here, what you can do is you try to count the carbon so you can have the lowest possible number combination for your locant. So maybe you can do 1, 2, 3, 4, 5, 6, 7. So this is obviously heptane. Okay. This is obviously heptane. And then you can try to count it from here. So you can have a lowest possible number combination is 1, 2, 3, and 4, and 5, and 6, and 7. So you can have 2 and 4. This is where you can find the methyl group over here, right? I didn't write it, but by now you probably see that just the one methyl group there, and also bromo group here. So even though bromo is in number 5, locant here, I'm gonna put the bromo first. So I'm gonna write 5 bromo, and then there's a 2 methyl group, so it'll be 2 and 4 dimethyl. So the thing is, even though there's the looking for the substituting groups, I know this will be higher than these two, but when you order the substituting groups, we always follow the alphabetical order. That is why, even though this is in number 5, I'm gonna put the bromo because B comes first, then M over here. So once again, you don't have to think about the di or tri as an alphabetical order, but it's actual substituting group is methyl, is N. So we're gonna write in this one. Makes sense, right? Good. So there's a couple more things. If you have a more than one substituting group like this one, so you have a bromine, chlorine, and they use methyl group over here. So in this case, what you can do, 7, right? So we have and it's either way. If you count the carbon from here or here, it's the same combination. It'll be 2, 4, 6, 2, 4, 6, 2, 4, 6. Okay. In this case, I'm going to choose to count the carbon from left to the right because in this way, even though they share the same combination of numbers for either way, you count the carbon in the compounds. But if you count the carbon from here, this is where you can have alphabetically prior group, the substituent group can have a lower number. So that will make 2 bromo, 4 chloro, because B and C, right? And M, and there was a 6 methyl. This is one more thing I want you to remember. So if that is the case, what we can also do whenever you have this type of situation, this is flowing, this is the here. So in this case, you're going to count the carbon from here, not here, because to give a number which is lower for the alphabetically prior group, which is B, which is a bromo. So it'll be 2 bromo, 4 methyl, pentane. Now 2 methyl, 4 bromo, pentane. Because in this way, we can give the lower number for the locant for the alphabetically prior halogen or any substituting group on your compounds. Make sense, right? Perfect. All right, so I'll move. It's okay, right? I'll move on. There's only one more thing I want to point out here. So whenever you're thinking about some compounds that has halogen as a substituent group, we call this Otg I halide. So you can think this is like, as a halogen group, maybe sometimes your halogen substituent group can be even more important than your actual compound sort of thing. I don't know, it's still kind of debatable, arguable content here, but because of this one, the halide sometimes become very important sometimes. So even though you know this is this way, right? And then this is going to be iodine, but also ido, right? Ido. This one carbon is methane, right? But if you want to put a more importance of this one instead of the carbon here, you can also say methyl iodine. So because either way is fine for halogen. Because sometimes, as I mentioned, it's just the way you put the more importance on which group and all things. So either is fine. So in this way, if you have maybe this one, same. You can call this 2. You can call this 2-chloropropane, right? You can also call this isopropyl chloride. Same thing, right? So one more thing. This could be bromocyclohexane. If it's a ring structure, once again, you don't have to put number 1 because we know we always put number 1 for the first only one group there. So it'll be bromocyclohexane, but you can also say cyclohexyl bromide. Okay, so it could be bromocyclohexane. You can also say cyclohexyl bromide. Either way, so this is one additional rule you need to memorize from other regular nomenclature we learn for alkane, and alkyne. They're pretty much similar, right? But this is another thing you just need to. Doesn't really matter which one you use. I really don't think it's anyway. So whenever you look at the chemicals in the lab, they either are way, but don't be confused. They're pretty much the same. Right? Makes sense, right? So I'll move on to actual reaction here. So if you look at the chapter 6, we talked briefly about the radical reactions. So radical reaction is unlike a polar reaction, they're only going to move one electron by one step from the paired electron where we initially saw the bonding inside in the compound. So one example I gave you in chapter 6 was this one. This will make this one. So basically, there's all the different steps. Basically, you break the bonds like in a one by one. So it's a radical breakage here. And this is simply also same as this one, right? So here, okay. And then later, this one comes radical. This also comes radical, which they are quite unstable. So they're going to do bond. This one, there's the one hydrogen radical comes to one of the chlorine radical comes to this one. So basically, this is what's happening over this type of radical reaction here. And then the scientists actually wanted to do more radical reaction with the different types of the alkene. So I'll give you several more. This is just a quick reminder as one example of radical reaction. So whenever we have this one, maybe you can have a butane. Okay. Let's try to do the similar reaction. Let's try to do the similar reaction over here. And then they try to find the two main product over here, which was two chlorine. This is the first one. The other one was this one. Okay. So as you can see, this comes in now on there's two terminal position. There's where you can find the two carbons at the end. Okay. So if they bond to either one of the terminal carbon here, will form this product here. If this chlorine bond to internal carbons here, that will become like this one. This is number two, number one. Okay, those are the one is the number one. There's the number two. So that means they're going to break the hydrogen on the internal carbon, either terminal one. That's why you're going to have two types of the products over here. And they saw the ratio between these two was about 30%. This one was 70%. Okay? So now the scientists were thinking, oh, why is it so different here? And they tried to actually find out, just do by individual hydrogen. So what I'm saying that is, this is where you can find the terminal carbon, where you can find the 6 hydrogens, because there are just 3, here are just 3 over here. So in total, in the terminal carbon, you have 6 hydrogens. For internal, we do the same, but these two has 2 hydrogen for each. So there's 4 hydrogen in internal carbon over here. So one of the hydrogen need to break the bonds to make a bond to chlorine over here, right? So technically speaking, this ratio actually tells you this one. If there is 100 numbers of product made from here, there will be 30 of them will be in this product. 70 of them will be in this product here, in the 70. And so maybe we'll do this for individual hydrogen, which you can find the 6 over here, which can have 4 hydrogen over here. You see that, right? Then for individually, each hydrogen on the terminal carbon is about 5% reactivity over here. Right? Because for one of the hydrogen, like here, but not just the one, but there's 6. So we divide by 30% by 6. So we can say approximately 5% for each individual hydrogen on the terminal carbon, we have this much reactivity here. The same thing over here, this is about 117.5%. So this actually tells you the hydrogen that bond to the internal carbon will tend to more be broken, so they can have a more new bond to the chlorine here. Okay, this is one case. And also they did more different compounds. So you have you have this one over here. So same thing, okay? And then you're going to have this one, which is the internal carbon hydrogen breakage and also new form. And this is another one that actually makes one of the terminal ones on the side. Doesn't matter which one, I'll choose this one here. Okay? And this one was about 35%. And this is 65%. So you might think, oh, maybe this is more major product, which maybe chlorine wants to bond to the terminal instead of internal, which is wrong. Because once again, you need to think about this one as, this one as the individual hydrogen. In internal carbon, the only thing that really bond to the carbon inside is one. Only one hydrogen can be replaced by what? Chlorine over here. So this is 35% over 1. But you have a 9 hydrogen on 3 terminal carbons. So this one actually has to be divided by 9 for individually, right? So technically, this hydrogen have about 35% reactivity. This same one is about 7.2%. So which is a lot higher. It's I think it's very high, much higher. So now you see why we're doing this, right? That means the hydrogen that bound to the carbon that has more substitute with R groups will be easily broken. So they can have a more easily make the new form to the halogen groups more easily because it's much higher reactivity in that hydrogen. Make sense, right? You don't have to understand the mechanism, but only thing you need to really know for the exam is this one. I'll show you the trend chart real quick. So what you really I want you to know is this one. So if you have a carbon has only one R group here, we call this primary because there's only one R group attached to it. This is a primary carbon position here. So if that is the case, we can do 2 now. So there will be secondary. If there's a 3, there will be tertiary, right? It's the same. So if that is the case, what you can say is the reactivity goes higher when the carbon is more substituted, and the hydrogen will be tend to more easily broken. That means reaction will happen much faster, more frequently. Makes sense, right? So if you look at the trend of the reactivity, the reactivity will be higher if you go from left to the right. So if you have a more substitute carbon that hydrogen is attached to it, you're going to have a more, the product will even, the product making will be much faster and more frequently happening. So this is the kind of trend over here. Let me add a couple more here. Okay, so this is the, maybe you can go even further, that with only hydrogen, right? So it's just, we can say it's a methyl position of the hydrogen. And then there's another one here, which we call this maybe we can say there's a hydrogen here that attached the carbon with another carbon at the double bond here. We call this the vinylic position of the hydrogen here. So this is the carbon that hydrogen is bound to the one of the carbons in a double bond. So this is a vinylic position, methyl, primary, second, tertiary, and then we have one more thing over here. If you have this one, so it's not the carbon on the double bond, but it's a neighboring carbon from the carbons in the double bond, and there's a hydrogen attached to the neighboring carbon to the double bond. We call this alylic position. Okay? Alylic position. So this is kind of a reactivity trend you find over here. If you go from left to the right, they're going to show you much higher reactivity to the halogen groups over here. So this is the what we found from the experiment here. Okay? So this is the reactivity trend table, but this also goes with the same, with the stability trend of radicals. So let's try to make the radical here. That meaning you break this bond here. So one of the bond between carbon and hydrogen, break it. So, but they break it like in a radical form. So they're going to have a 1 by 1. So hydrogen take 1, carbon take 1. So this will become, okay, this position. So there'll be one radical form over here. Same thing over here. Okay. So they all just break the one bond between carbon and hydrogen, but it's a radical breakage. So there will be radical form after they lose the hydrogen over here. And if you look at this one here, stability trends of this radical also goes along with the reactivity trend too. So that means if you go from left to the right, this is the least stable. This is the most unstable form. And this is the most stable radical form among those. Okay, so it actually kind of makes sense if you try to make a reactivity on the one without they do the radical breakage. But when they do the radical breakage and they make a radical form, if it's more stable when it's in the radical form, they tend to break the bond more easily. Because even though they break the bonds, the radical form will be not that unstable. Then they don't mind breaking that bond radically. Kind of makes sense, right? But if you look at the vinylic form here, this bond, if they break apart and now become a vinylic radical form here, this is very unstable. That means they don't want to break the bond because they don't want to be unstable. So that actually kind of makes sense that whenever you try to do it more, the energy diagram wise, this only takes about 760 kilojoule per mole to do it. This is about 400, 410, 421, 439, 465. See, this energy is going up to break the bonds. That means they don't, if you go from the left, this is the one that want to break the bond. This is what we need to put a lot of energy into it. But this one, they don't really mind so much. They can, okay, I can break it. So you don't have to put a lot of energy here to just break it, because whenever they do the radical breakage, radical forms stay unstable, but relatively speaking, they're quite actually more stable than the others. So they don't mind to putting a lot of energy. I mean, they don't have to have a lot of energy to break the bonds. And it kind of makes sense in the terms of the stability trends, reactivity trends on the radical form and reform. Yeah.
When we were in Gen Chem and we were doing entropy of formation, and we were calculating like the when bonds would break and things like that, which value would we end up using? Would we use it related to these radical reactions, or is it an average, or is it
for the reaction wise?
Yeah.
Yeah. So this is like a experimental proof that how much energy will be used for mole, the kilojoule for mole. So this is how we find out why this is more reactive and the other is not. So this is only the experimental proof, but this form is just one of the example why it's more stable, that makes the reaction goes much higher speed or something like this. So absolutely you don't have to memorize those numbers here, but all I want you to remember is just the trends. So for example, that's a very good question. So for example, if I give you, so in your exam, if I give you the problem like this one, and particularly this position of the hydrogen, if they do the same halogenation process right here, this one will be much faster for this position. So if it's number 1, if it's number 2, you need to choose number 2 for specific position with the hydrogen. Are we not sure for the other, but for the specific position you should know because we just found this. So this is something you may see on the exam 2 and also the final exam. But it makes sense, right? If it's more substitute, the hydrogen can be easily broken because that radical form after breakage will be a bit more stable than the other, relatively speaking. But the relative position was kind of a unique one. Also magnetic position too. That's why they specifically talks about this one in chapter 10. So if that is the case, I'm going to explain why is the case, why is the case, but you don't have to know for the exam, obviously. You just need to know what will happen when you do the lytic bromination happens in your compound. So whenever you have this type of lytic position happening here. So once again, this is a position where you can find the neighboring carbon, not the carbon itself. That will make your vanillin position. But this is a lytic because that is the radical on the carbon neighboring from the double bond, which is 2 carbons there. But one thing they do here is they also do a bit of like a resonance structure over here. Oh, I do the same thing. So if that is the case, they can either go this one. The reason is if you remember the double bond, they're going to store the pair of electrons in here and here. But there's one electron over here, the P. So if they can go either left and right, because they can do this one. This one. So electronically speaking, they shows the evenly distributed electrospin on the both sides of the compound. That makes this lytic radical compound quite stable. It's still not stable because it's a radical, but electronically wise, they have a bit of a. So this, I know this is a kind of confusion. So this is the where we can. I'll remind you something. I remind you one term I gave you, if you took my class in Zen Chem 2 was delocalized. Delocalized electron. So this is where you really can, well, you don't mind where the electron really is, because if you look at this one as like an orbital, you know the orbital, right? This is the way you can find the electron by high chance. In this case, we don't care anymore about where the electrons really are on those carbons here. So maybe you can say there's a double bond. We know in this space there's a 2 pair of electron for sure. There's 1 pair. But when it's delocalized by showing the similar electrospin evenly distributed on both sides of the compound, they become more like a material rather than just material, like a particle, like a wave, like a lightning. So anyway, if that is the case, it kind of makes sense that it actually makes quite a stable radical form, even though it has odd numbers of electron, which kind of not so good with the Pauli exclusion rule and everything. So anyway, if that is the case, where makes sense, right? Okay. So if that is the case, there is an actual problem that I'm going to tell you. You might see on the exam is this one. So if you have 1 octene, okay? So you have a 1 octene here, and this time we're going to treat it with a special compound to prevent some unnecessary bromination. We call this MBS. So we have some. We're gonna treat with a bit of something. Some organic compounds here with a bit of a light, but this is what you can do. So in this case, what you really need to do is try to find the lytic position of the hydrogen. So if this is the carbon here and here, the lytic position is actually here, not those here. Those are the way you can find the vinylic position, which is the most unstable when it's break, so they don't want to do it, but here is quite okay. So what you can do whenever you do this, we're going to attach here, okay? And where you can find the lytic position here. So this is your product after this. Here's one more thing. Like I mentioned, they can go either left to the right, right? Double bond goes left. So this is a one way whenever you have this one. But you can also have this one. Can you guys guess why? Like I said, this one has a lytic position you can have, right? But I told you before, this is more like a resonance kind of mechanism over there. So they can either do this one too. This is why you can have a one as possible product, but this is also possible too. And technically, this is actually even major product because the whenever they come into this part of the compound, they're going to experience the less hindrance anymore. But only thing that I want you to remember for the exam is there are going to be two possible products from here. If we choose only one compound in the multiple choice, you're only going to get a half credit because this is another one that you may choose on the multiple choice. This would make sense, right? Okay. If you this will not be on the exam, but I will just do this for your understanding. Okay. So if you have ring structure instead of just the primary alkyl group, you have this one over here. You can treat it with the same thing. Okay. Then I'm not gonna do all the drawing because you don't have to know. But there's not two but four, because think about this one. A lytic position here is when it's here, it can be right here, right? Because the neighboring carbon right here with the double bond. Also here, too, right? But like I said, if it's do bit of a resonance structure, they can also do this one. You see, right? The double bond can be in here. They can do this one. Also, this is the ring structure, so they can actually go in this way too, and here as well. So you actually 4 different products can be possible because it's a ring structure, and also that double bond will do more like a lytic position. There would be more like resonance like compound, but it's a ring, so it can go either up and down. But so there's the 4, not 2 in this case. But this won't be on the exam. But the one before, I told you, they still need 2 because it's a primary. So that will be for sure something you may see on the exam. Okay. Let me see. Yeah, I think I'll just stop here because in the morning class, I covered this one. It took me so long, but it actually finished quite early. So I'll just stop here. So I'll try to cover the other half of the chapter 10 Wednesday. That means we may be able to cover chapter 11 from Friday, and then I'll try to save the 2 remaining lecture next week for the review. So same thing here. Do you remember this? Like you have to watch the last 2 lecture as a review session for your exam 1. I'll do the same. So whenever we have an exam on the week before the Thanksgiving week, so make sure you guys watch those the 2 last lecture for as a review. Will be very helpful and efficient way for you guys to study. But basically, I know it's a lot of things you need to study during like chapter 6 to 11. There's a lot of mechanism, a lot of reaction you need to memorize. So to make your studying much easier, like I told you so many times in the previous weeks, and even still again, you don't have to know the mechanism. You need to study the mechanism for your understanding. That will make you much easier to understand and memorize the reactions. But only thing you really need to memorize for the exam is the what makes what product. That's all. And it's only going to be one step. And then there will be one there will be one extra credit exam. Extra credit question at the end of exam 2. That will be only thing you need to do multiple steps. But I already told this in the Monday lecture. So if you take a look on the YouTube channel, exactly the same problem will be on the exam 2. So if you just memorize that, you get an easy extra credit right there in exam 2. So, and also, I'll probably post the extra credit quiz by tomorrow on campus. I'll also make an announcement for it too. But that's from us. All right. Thank you guys. I'll stop here today.